A fine-tuned model handles every message on format, polite, fluent, then hits a multi-step problem and confidently returns the wrong answer. More fine-tuning is the instinct. Whether that instinct is right is exactly what separates engineers who've shipped this from those who haven't.
Let's start at the basics. What does SFT actually change about a base model mechanically, and what does it leave untouched?
SFT reshapes the model's surface behavior. It learns the instruction response format, the expected tone, the habit of actually answering the question rather than continuing the pre-training document. What it doesn't touch is the underlying knowledge. The Lima paper made this concrete. A 65 billion parameter model, fine-tuned on just 1,000 carefully selected examples, outperformed models trained on 50,000. The researchers' conclusion was that almost all knowledge is learned during pre-training. SFT teaches the model which register to speak in, not what to say. Think of it as an interface upgrade. The base model already speaks the language. SFT teaches it to pick up the phone when you call. That distinction matters the moment you're debugging why a well-fine-tuned model still fails on hard tasks.
Good, let's talk about data quality then. Given that framing, if the knowledge is already in the weights, why does SFT data quality matter so much? What's the wrong way to think about it?
The wrong way is treating it like a volume knob. More data, more coverage, better model. It doesn't work like that. Each training example is teaching a formatting habit or a response pattern for a specific kind of task. If your 1,000 examples span a broad, diverse set of skills, writing, reasoning, structured QA, coding, the model generalizes the underlying instruction-following behavior. If your 50,000 examples are slight variations of the same customer service template, you've over-indexed on one narrow register, and the knowledge for everything else is still locked in pre-training weights, inaccessible because the model never learned to express it in that context. The Lima metric for quality was really diversity. Each example should demonstrate a pattern the others don't already cover. Redundancy adds noise, not signal.
Right, here's a concrete failure. Polished format, confident wrong step 3, never self-corrects. Here's a failure I've seen in practice. The model is polite, format is clean, but it makes a confident mistake at step 3 of a multi-step math proof, and never catches it. Would more SFT examples fix that?
Probably not, and understanding why is the crux. SFT trains on static expert traces using cross-entropy. Predict the next token of the reference answer. What the model never does during training is generate a prefix, realize something's off, and try a different path. It sees the correct answer but learns to imitate it, not to discover it. That's the same behavior cloning limitation known from robotics. The model learns the shape of correct reasoning chains without learning how to search for them. When it makes a step 3 error at inference time, there's no mechanism to catch it, because nothing in the objective rewarded detecting and correcting errors mid-generation. More clean SFT data teaches the model what correct reasoning looks like. It doesn't teach the model how to recover when it goes off track.
Say the team pushes through 50,000 examples, loss converges, evil barely moves. Say the team pushes through anyway, 50,000 curated math examples. Training loss converges cleanly, evil accuracy barely moves. What's happening?
The classic symptom of objective mismatch. SFT optimizes imitation of one reference trace per question. But at eval, you're measuring whether the model gets the right final answer, and there are many valid paths to that answer, most of them not in your training set. So the model gets better at reproducing the exact demonstrations, and worse at generalizing to variations it hasn't seen. There's also a subtler issue. Recent work found that even after training loss converges, models frequently fail on their own training examples. They can't reliably reproduce the demonstration they were trained on. That's incomplete learning. The objective doesn't actually guarantee the behavior you want. And more data in the same distribution just pushes the model further into a regime where imitation diverges from correctness.
Given all that, let's talk about the diagnostic for switching away from SFT. Given all of that, when do you stop adding SFT data and reach for RL or preference optimization instead? What's the diagnostic that tells you it's time?
The cleanest diagnostic is, can the model produce the right answer anywhere, under different sampling temperatures, prompt rephrasings, best of 10? If yes, it has the knowledge and just won't reliably choose it. That's a preference problem. DPO or RLHF can steer which completions get reinforced without needing a live reward signal for every query. If no, it fails consistently even with generous sampling, that's a capability gap, and the fix is more pre-training or a larger model, not preference tuning. The third case is verifiable correctness, math, code, structured reasoning. There, RL with outcome rewards, GRPO style, can optimize directly for what you care about rather than for imitating demonstrations. The signal is, the model knows the answer exists but won't find it reliably. That's exactly the regime reward optimization is built for.
So, pulling the thread, SFT shapes format and unlocks instruction following, but it doesn't add knowledge and it can't teach a model to search its own reasoning. When training loss converges and eval won't move, that's the signal to stop imitating and start optimizing for outcomes. If this kind of prep helps, like this episode, share it with someone who's interviewing and subscribe to Interview on Your Way. More and better questions are on the way.